Okay, so we're moving to problem number 14, and they ask for the points of inflection and discuss the concavity of the graph of the function. So now we're going to set up our table, which in this case we'll be talking about concavity instead of increasing or decreasing functions. But so when we did increasing and decreasing, we took the first derivative and set that equal to 0. In this case, we're going to take the second derivative, set that equal to 0, and then set up our intervals. So this first derivative is going to be 8x cubed minus 8, and the second derivative is going to be equal to 24x squared. So we take the second derivative and set it equal to 0, and so what's going to happen? Well, it's 0 when x is equal to 0. So we're going to check the concavity on either side of x equals 0. If we go over to our graph, you can see something weird is happening here. I mean, this is concave up, and so maybe this changes to concave down at this point. Don't know. It might not. It might just stay concave up. It's so straight that it's really hard to tell visually what's going on. Now there's a way we could go back to the graph and try to figure it out. But so now we're going to set up our table, and since I didn't want to add a page there. So I'm going to make it my table, and we only have one possible point of inflection. We have one point of inflection. So we only need 2 intervals, and we need 4 rows. So just like we did before, we do that. So we have the first row, which is interval, same thing as before. And what we do is we go from negative infinity to our point of inflection, which is 0, and then we go from there to positive infinity. So we have the test point. So I pick something, -1 sounds good, and +1 sounds good. So those are in the intervals. Then we do the same thing, but we look at the sign of f double prime. So we go back over here to this expression. So f double prime of x is equal to 24 times x squared. Well, any number squared is going to be positive, so we could say it's positive, and then we can make the conclusion that it's concave up in both cases. So if we go back to the graph, it looks like it just about goes to 0 concavity there, but then it'll start to curve up again. There'll be a curvature in that direction. So this is still concave up based on this. Now if we had something like 2x to the 4th and then had a like plus 7x squared, we might then have an actual change in curvature at that particular point. Number 19. So our function is x divided by x squared plus 1. And below you can see the graph. So if we were to just look at it graphically, what I would see is I would see the curve bending down. So the inside of the curve is that way. At some point here, I'm not exactly sure where, it changes and it starts pointing upward. The inside of the curve is there. Then we cross 0, and it's now the inside of the curve is downward. And then at some point, you can see that it starts to bend the other way. So we're probably going to have 3 points of inflection somewhere in this area where the concavity changes. So we'll see what happens. Come back and look at this later. So we take the first derivative, and I'm going to change it to h again just because it's a quotient. So we take, let's say f of x is the numerator, g of x is the denominator. So we take the derivative, of each. And then we use the quotient rule. So h prime of x is equal to these two multiplied together. So we get 1 times x squared plus 1 minus x times 2x, all divided by x squared plus 1 quantity squared. And so up here we get x squared minus 2x squared, so we get negative x squared plus 1. 1 times 1 is 1, x squared. 1x squared minus 2x squared is negative x squared. Okay, now we take the second derivative. So we're going to, again, define the numerator as, I'm going to change it to 1 minus x squared so that the positive term is first. G of x is equal to x squared plus 1 quantity squared. So f prime of x is negative 2x. And g prime of x, in this case I'm actually going to just use the chain rule. So what you'll end up with is 2, the exponent, times the quantity in the parentheses, reduce the exponent by 1, and then multiply by the derivative of the object in the parentheses. So what you'll get is 4x times x squared plus 1, which is the same as 4x cubed plus 4x. So that's g prime of x. Now we use the quotient rule, so we can say h double prime of x is this times that. So you get negative 2x times x squared plus 1 squared minus f of x, 1 minus x squared, times g prime of x, which is 4x cubed plus 4x, all divided by x squared plus 1 to the 4th power. So when we square this, we'll get that to the 4th power. So basically, the second derivative is going to be 0 when the numerator is 0. The denominator never goes to 0 because it's squared. It's to the 4th power. So we square any number here, so that's positive, and then you square it again, so it's really positive. So all we have to do is take the numerator and let us, so I'm going to expand this out, so you'll get x to the 4th plus 2x squared plus 1. And then we have the second term, which I'm not going to multiply out yet. Well, in just a second. Okay, now we're going to multiply that. So here we use the distributive property. So you get negative 2x times x to the 4th is negative 2x to the 5th plus negative 2x times positive 2x squared, which would be negative. So we'll get negative 4x cubed minus 2x. Okay, I get a minus sign, and then we multiply this out. So we get 4x cubed, and then in the middle we get minus 4x to the 5th, and then the outer plus 4x, and then we have minus 4x cubed, and that's going to equal 0. So let's see if there's anything we cancel out. Well, you've got negative 4x cubed, and you've got a negative times a negative is a positive, so that's these two. This is going to cancel out with that, except we still have this one left. So actually it doesn't quite cancel out. We still got this part left. So let's combine their terms. We've got negative 2x to the 5th minus 4x to the 5th, but actually you're adding it. Negative times negative is positive. So we get positive 2x to the 5th. We don't have any x to the 4th terms. We have minus 4x cubed from this term here. So let's just kind of check them off as we go. So we got that and that term taken care of. To get that, we have this term to get that. And then we have negative 2x minus another 4x, because you got negative and negative, so you get negative 6x. And that equals 0. So we can divide by 2. So we divide everything by 2. And then we get factor out an x. So we get x times x to the 4th minus 2x squared minus 3 is equal to 0. Okay, so now we factor this, and because this is 4th, this is squared, and this has nothing, we can factor it out as such. So you'll get x squared here, x squared there, and we need negative 3, so it's going to be 3 and 1, and we're going to put the negative sign here and the positive sign there, because we'll get negative 3x squared plus 1x squared, which gives us negative 2x squared, and negative 3 times 1 is negative 3. So that's how we factor out the second derivative, the numerator of the second derivative. Well, this never goes to 0 because this is square. This is always positive, and you add a positive number. So this term, this factor, never goes to 0. So the other two, so our solutions are going to be, or our values where f double prime of x equals 0, are at x equals 0, and the other one is x equals minus the square root of 3, and x equals positive the square root of 3. How did I get that? Well, if you set x squared minus 3 equal to 0, add 3 to both sides, take the square root, you get x is equal to plus or minus the square root of 3. So there you go. So those are our 3 points of inflection. Points of inflection. Actually, possible points of inflection. So now what we're going to do is we have three of those, so we're going to need 3 plus 2 is 5, a table with 5 columns and 4 rows. 1, 2, 3, 4, 1, 2, 3, 4, 5. There it is. So I'm going to try to make this as big as possible. And our first column is the headings: interval, test point, sign of f double prime, and a conclusion relative to concavity. So our intervals, negative infinity to negative the square root of 3, negative the square root of 3 to 0, 0 to positive the square root of 3, and positive the square root of 3 to positive infinity. So that covers everything. The only changes occur at these possible points of inflection. So now we pick test points. So square root of 3 is 1.7 something, 1.732. So I'm going to pick negative 2, pick negative 1, positive 1, positive 2. If we go back to our expression for the second derivative right here, you can see that this term is always positive. So all we have to do is look at the sign of the numerator. And so that's what we have. But we can actually use this simplified version, even this simplified version, because let's make sure we're, I didn't change any, I didn't divide everything by -1, so everything should be, the sign of this should be the same as the sign of that. If this is positive, then that should be positive. So let me just copy this thing right there. I don't understand why it copies sometimes. It doesn't copy. Yeah, it doesn't show up as, if I clone it, it'll work. So I'll just clone it and drag it over from one thing to another. Okay, so that's the equation we're talking about, and what we're doing is the second derivative, f double prime of x, is proportional to that. Okay, because we divided by a number. So what we have to do is determine whether this is positive or negative. So I'm just going to plug in for x equals -2. What do we get? We get -2 to the 5th minus 2 times -2 to the 3rd power minus 3 times -2. So we'll get -32. Here we get +8, or -8 times -2 is +16. And then we get +6. -32 plus 22 is -10. Now, another way to look at it on these extremes here is you could just say, well, let me put a negative infinity. How do you do that? Well, when you get to infinity, these terms drop out. So these are insignificant. So you just look at the highest order term, and if you have negative infinity to the 5th power, it's still going to be negative. If it was negative infinity to the 4th power, it would be positive. So it's going to be negative, which agrees with what I have here. So that one's negative. And then we could do for x equals -1. Can't really use the same argument for this part. So we'll get -1 plus 2. -2 times -1 is +2. -3 times -1 is +3. So that becomes +4. It's positive. So it's positive up here. For x equals +1, we'll get 1 to the 5th minus 2 times 1 cubed minus 3 times 1, which is 1 minus 2 minus 3, which is -4. So at x equals 1, you get negative. And again, you can use this order of magnitude argument. When x is positive, when x gets really positive, these terms become insignificant relative to this first order term, this first term. And so something positive raised to the 5th power is positive. So now we can talk about the concavity. So we're going to say this is going to be concave down. It's going to be concave up, concave down. I'm just looking at the sign of the second derivative. Concave up. Okay? So let's go back to the graph and see if that's right or not. So I'll put this on one page so we can see it. So what the second derivative test said was that at 3 points, x equals 0, x equals the square root of 3, negative the square root of 3, which is 1.7 something, about right there. Negative 1.7 and positive 1.7, about right there. Those are where we could have possible changes in concavity. So that's what the second derivative test told us. Then what we did was we broke it up into intervals. We went from negative infinity to negative the square root of 3. We went from negative the square root of 3 to 0. We went from 0 to positive the square root of 3. And we went from positive the square root of 3 to positive infinity. So those are the intervals. So that's one interval. Second interval. Third interval. Fourth interval. So those are the 4 intervals. Then we did the test points. So we picked -3, -1, +1, and positive, actually it wasn't -3, it was -2. So those were our test points. I'll just call them TP, TP, TP. So those are 4 test points. Let's just confirm that. Okay, those are our test points. -2, -1, 1, 2. And when we evaluated the second derivative, not the first derivative, we found out that in this interval that f double prime of x is less than 0. Here we found in this interval that f double prime of x is greater than 0. In this interval, f double prime of x is less than 0. And out here we found that the value of the derivative is greater than 0. So because of this, we said because of these, this is up, down, it's less than 0. So this means down, concave down. This means up. This means down. And this means up. And we can see that's the case. This is concave down, concave up, concave down, concave up. Okay, so we're going to section 4 now. And section 4 deals with what's called concavity. That's not whether it's increasing or decreasing, but is the slope increasing or is the slope decreasing? So it's to do with the curvature of the object and not whether it's increasing or decreasing. And we use the second derivative to figure that out. So anyway, problem number 2 says determine the open intervals on which the graph is concave up or concave down. So for critical numbers, we set the first derivative equal to 0. For the curvature, we look at the second derivative. So in our particular case, problem number 2 is you get -x cubed plus 3x squared minus 2. So that's the function, the original function, which you can see on the graph in the book. And so looking at the graph, concave up is going to be from -infinity to, it looks like about x equals 1, and then it curves the other direction, so it's pointing, the curve's pointing downward. So that's how you would do it, just by looking at the graph, but we're going to do it by taking the derivative. So we take the first derivative, and we get -3x squared plus 6x. This drops out because it's a constant. And then we look at the second derivative, and we get -6x plus 6. So that's the second derivative. And then if you set the second derivative equal to 0, the equation for the second derivative said equal to 0, just like with the critical numbers, you set it equal to 0, and then you solve for the values of x. So you can see that it's the same as 6x minus 6. If you divide by 6, you'll get x minus 1 is equal to 0, or x is equal to 0. So this is the what we call the point of inflection, the x value, where it changes from concave up to concave down. So if you look at the graph, you can see that's what I said. I said it changed concavity between, but I'm going to plot the graph and I'm going to bring it over. You can't see it right now, so don't worry, but it'll show up here in just a second. So I'm going to plot this function, -x cubed plus 3x squared minus 2. Okay, there it is. Graph it. There it is. Looks just like the book. Take a picture of it. Okay, voila, there it is. So what we said was the second derivative is equal to, and it's in pi, which I didn't see it in pi when I took it, but I see it there. Okay, so let me Let me just redo that. Take it off of pi because we're dealing with trig functions. Okay, we'll do it again. Okay, so there it is. Let's put it on page. So it says that x equals 1 is the breakpoint. So we have, just like critical numbers, we break the interval up. And so what we have is an interval from negative infinity to our possible point of inflection. So let me make that clear. So where the derivative is equal to 0 is a possible point of inflection. It's not necessarily a point of inflection. So these are, I can't, I'm driving that in wrong. So those are the two intervals. So what's concave up, concave down? Well, see how it's bending? So it's bending the inside of the curve. You were taking the curve is pointing upward. It's pointing to the right too, but it's pointing upward. And likewise here, if the curve is bending this way, so the inside of the curve is down. So what we would say is we have concave up in this interval till we get to this point, then it switches the other way around, and then we have concave down. And this is where f double prime of x or y double prime is equal to 0, is this x equals 1 value. Okay, this is problem 21. It's a trig function problem. And again, it's asking for find the points of inflection and discuss the concavity. So here's our graph, 0 to 4 pi. You can see we have concave down here, we have concave up there, so and we have a change at that point. So that should be our solution. And also at the ends as well. It's going to go that way, and it's going to repeat itself. So how do we prove that's true? Well, we take the second derivative. The first derivative is going to be 1/2 the cosine of x over 2. Why is that? Well, this is the sine of 1/2 x. So our coefficient is 1/2. So hopefully by now you have recovered from the first test or the second test, and now you know to take the coefficient, which in this case is 1/2, move it outside, take the derivative of the sine, which is the cosine, leave the argument the same. So then we do it again. So we'll get 1/2 from here, and another 1/2. We take the derivative. The derivative of the cosine is negative the sine, and the argument doesn't change. So f double prime of x is equal to 1/4, negative 1/4 the sine of x over 2. So the question is, what do we do? Oh, well, we set that equal to 0. That's what we do. So we say negative 1/4. When is the second derivative either undefined or equal to 0? Well, the sign is always defined. So we set that equal to 0. And if you divide by negative 1/4, you still 0. So the question is, between 0 and 4 pi, where does the sign equal 0? So let's think if we can do this using our reference angle stuff. So where's the sign? Let's just do the sine of x first, and we'll go, if we just do x, we will be going between 0 and 2 pi. So in this one, because it's actually on the axis, the reference angle thing doesn't work as well. I mean, it's a little harder to understand, so you just have to think about this. If you have a unit circle, when is the sine of the angle equal to 0? Well, it's where, remember, y is equal to the sine of theta for the unit circle. This is theta. So where is y equal to 0? Well, it's equal to 0 there and equal to 0 there, which is, so we know, therefore, the sine of x is equal to 0 when x equal, well, let's use theta instead. Let's just go back up here. Do it all in terms of theta. You'll see why in a second. Sine of theta. Sine of theta is equal to 0. So when sine of theta equals 0, when theta equals 0, pi, and 2 pi. But in our case, theta is equal to x over 2. So this is going to be true when theta is equal to these three values. So we can take the three values that we have. So we're going to say x over 2 equals 0 when x over 2 is equal to pi, and when x over 2 is equal to 2 pi. So all we have to do is multiply by 2, and you'll get x equals 0, x equals 2 pi, and x equals 4 pi. So those are all the values of x in the original equation, which we had x over 2. Those are the values of x, where the second derivative is 0. 0, 2 pi, and 4 pi. So that's what we're going to set up our interval based on these numbers right here. So we have 1, 2, 3, except this is the beginning of the interval and this is the end. So really we just need 3 columns plus 1 for labels. So we need 4 columns and 4 rows. And I should put that on the other page. So here it is. So in our case, our intervals, let me put them on page so you can see better. So we have interval, we have test point, we have the sign of the second derivative, and we have the conclusions. So our intervals are from 0 to 2 pi, 2 pi, actually I think we only need 2 columns. Yeah, 2 columns. 2 pi to 4 pi. Don't need this one. So a test point would be, well, that's pi looks like a good number, and here 3 pi. And the second derivative was equal to negative 1/4 the sine of x over 2. So let's just plug the numbers in. So f double prime of pi is minus 1/4 the sine of pi over 2. Plug that in your calculator, and you find that the sine of pi over 2 is 0. Wait a second, no, it's not right. The sine of pi over 2 is positive 1. So positive 1, you'll get negative, positive 1 times negative 1/4 is negative, so it's negative. And if you evaluate the second derivative at 3 pi, we'll get 3 pi, which is x divided by 2. The sine of 3 pi over 2 is negative 1. So we'll get negative 1 times negative 1/4, which will be positive 1/4. So this is positive, this is negative. So this is positive, so this is concave down. And this is concave up. Is that true? Yes. Down, up. This is 2 pi. This is 4 pi. This is 0. So we're concave down from 0 to 2 pi, and we're concave up from 2 pi to 4 pi. Problem 26. So anyway, this is the function. Find the, I keep saying possible points of inflection. Is that true? Let's read the definition. If it is a point of inflection, if either the second derivative equals 0 or the second derivative does not exist. So I guess it is as long as the derivative doesn't have to have a change in concavity. You can have a point of inflection without having a change in concavity, but you can't have it the other way around. F prime of x is 1 plus 2 times negative the sine of x, or it's equal to 1 minus 2 sine of x. Okay, now what do we do? Okay, we take the second derivative, so f double prime of x is equal to, well, derivative of 1 is 0, derivative of the sine is the cosine, so we get negative 2 cosine of x. So that's the second derivative. Now the question is, what values of x does that equal 0? Well, the cosine of x equals 0. If you divide by negative 2, you get that. So the question is, at what values of x does the cosine equal 0? So again, rather than using the reference angle, this is a special case where we don't need to use it. We just draw a unit circle. We're just looking at the axes. And we'd say the sine of theta is y. Cosine of theta is the x value on this coordinate system. So when is the cosine 0? When x equals 0. When is x equals 0? X is 0 here, and x is 0 there. Everywhere it's either negative or positive. So based on that, therefore, x equals, this is true when x equals pi over 2 and x, or x equals 3 pi over 2. Those are my two solutions to this equation. And therefore we have 2 points of inflection. So we need 3 plus 1, 4 columns and 4 rows. So let's put this on one page so we can draw it a little easier. Interval, test point, sine of f double prime, and a conclusion. So our interval was from 0 to pi over 2. From pi over 2 to 3 pi over 2, and 3 pi over 2 to 2 pi. Because if you look at the problem, the interval's from 0 to 2 pi, so this whole thing has to span. And we have points of inflection at pi over 2 and 3 pi over 2. So those are our splitting points, and then you put x in between. So let's pick pi over 4. Let's pick pi. Let's pick 7 pi over 4, I guess. Or is it 2 pi, 3 pi? So that's the same as 6 pi over 4. So 7 pi over 4. So those are the points that are in those intervals, not at the end of the intervals. And remember the second derivative. Let's go back. What was the second derivative? Second derivative was this one, negative the cosine of x. So f double prime of x is negative the cosine of x. So the second derivative at the first test point is negative the cosine of pi over 4. And you just plug that into your calculator. pi over 4 is in the first quadrant, so the cosine of a number in the first quadrant is positive. We can actually just do this by using all students take calculus. So pi over 4 is in the first quadrant, so the cosine is going to be positive. So then you take the negative of that, you get a negative result. So this is negative. The second derivative of pi is negative the cosine of pi. Well, the cosine of pi is -1, so you get a negative sign times -1, which is +1, which is positive, so we put the positive in there. And the reason I didn't use this, because these are actually not, this one's not in the quadrant, it's on the axes. The other way I would have done that is, again, drawn my unit circle, and the cosine is the x value. So you can see it, pi, which is here, the x value is -1. And that's how you could do it using the unit circle. And then we have 7 pi over 4. So we get negative the cosine of 7 pi over 4. Okay, so the cosine is positive. This is in the fourth quadrant. So the cosine is positive in the fourth quadrant, so this is going to be a positive number. Negative times a positive gives us a negative, so it's negative. So the conclusion is concave down, concave up, concave down. Is that true? Down, up, down. Down, up, down. Down, up, down. At pi over 2, which is 1.6, 1.57 something or other, 1.57, which is right here. There's pi over 2. And then at 3 pi over 2, which is, what is 3 halves pi. 3 divided by 2 times pi, 4.7. So we go down here, 4.7 something, it's about right there. That's 3 pi over 2. So, like we did before, let's just set up our intervals are from 0 to pi over 2, pi over 2 to 3 pi over 2, 3 pi over 2 to 2 pi. So those are the 3 intervals that we put in a box. That's not right. It's pi over 2 to 3 pi over 2. And then x is between 3 pi over 2 and 2 pi. Okay, so those are the 3 intervals. The test points that we picked were pi over 4, which was about right here, at pi, which is about right there, and 7 pi over 4, which is about right there. So the second derivative at this green value of x was negative, so that's why we got concave down. At pi, we got a positive second derivative, which is concave up, and at 7 pi over 4, we got a negative second derivative, which was concave down. So that all works out. It's problem 31. And 31 says, find all relative extrema, use a second derivative test where applicable. So we are going to, so all you have to do is find the critical numbers, and then you evaluate the second derivative of those critical numbers and see whether it's positive or negative. And if it's positive, then it's pointing up, which means it's a minimum, and if it's pointing down, then it's positive. So you can see here's the graph. So we already know what the answer is. We're going to have a maximum here at 0 and a minimum here at 2, and this is concave down. second derivative is less than 0. And here it's concave up, so the second derivative is positive. So let's just do what we normally do. We take, we're going to take the first derivative and we're going to set that equal to 0 to find out what the critical numbers are. So when you take the derivative of this, you get 3x squared minus 6x. So now we're going to set that equal to 0. So if we divide by 3, we'll get x squared minus 2x equals 0. Factor out an x, and we get x times x minus 2. So we have two critical numbers. X equals 0 and x equals 2. Okay, there's x equals 0, x equals 2. So that makes sense. And then finally, all we have to do is evaluate f double prime at x equals 0 and x equals 2. So before we can evaluate, we have to actually figure out what it is. So f double prime of x is just the first derivative of the first derivative. So we go to the first derivative and we take the derivative again and we get 6x minus 6. So now all we have to do is what is f double prime of 0, which is the first critical number. So you get 6 times 0 minus 6, negative 6. What's the sign? It's like a game here. What's your sign, man? So it's negative. Negative 6. Therefore, it's concave down. Concave down. Looks like that. So therefore, it must be a max. Therefore, max. Okay. Then you do the same thing. F double prime of 2. 6 times 2 minus 6 is 12 minus 6, which is positive 6. What's the sign? What's the sign? What's the sign? What's the sign? It's positive. Positive second derivative means concave up, which means like that. That's a concave up. It's pointing upward. Therefore, it's a minimum. So so we know that x equals 0 gives us a max and x equals 2 gives us a minimum, and so we can just plug those in. So now what we do is we take the value of the function as 0. So the value of the function is x cubed minus 3x plus 3. So f of 0 is 3, because these just drop out. And then f of 2, which is the other critical number, is 2 cubed minus 3 times 2 squared plus 3 is 8. And then you've got 4 times 6 is 4 times 3 is 12, so you get minus 12 plus 3. And so that is negative 4 plus 3, which is negative 1. Did I get that right? Yep, negative 1. So let's go back and just check it out. Go back to the graph. Here's the function at x equals 0, y equals 3. Check. When x equals 2, y equals negative 1. Check. So that all works out. There's a point of inflection here at x equals 0. If we go back to the second derivative, set this equal to 0, which we didn't do. But if you solve for x, you'll get x is equal to 1. If we go back to our graph at x equals 1, it's that point right there, point of inflection. So it's concave down everywhere on this side, and after the point of inflection, everything's concave up. Okay, this is number 40, which I forgot to do, I guess, initially. This is the one trig problem. Well, maybe not the one trig problem, but we worked on very similar to this in class. So what we're looking for is find all relative extreme, use the second derivative test where applicable. And we're going in the interval from 0 to 2 pi. So basically we're going to take the first and second derivatives, and we can use the critical numbers to find the possible extrema. I'm trying to remember if I need to do the table in this case. I guess we will. We don't need to, but we'll do it just to be complete. Actually, we'll do both tables so that we just get some practice. But what we could do is we could just find the critical numbers and then use the second derivative test at those critical numbers to see whether we have minimums or maximums. So we'll do it the short way, and then we'll make up the tables if you want another example of how that works. Okay, so first derivative. It's going to be 2 cosine of x. That's because the derivative of the sine is the cosine. And the derivative of the cosine is negative the sine. But because we have cosine of 2x instead of just cosine of x, we use the chain rule, which means that the 2, that constant is out front, and you multiply by the derivative of this cosine, which is negative the sine. So that is the first derivative. And let's go ahead and calculate the second derivative while we're doing derivatives. So derivative of cosine is negative the sine. So the coefficient still stays as negative as 2, but we get a negative sign. And then the derivative of the sine is the cosine. But again, we get an extra 2 multiplied. So we'll have 2 times 2, which is 4. And we have the cosine of 2x. The derivative of the sine is the cosine. Because of 2x, we get another 2 multiplied by that out front. Okay, so those are the derivatives. So to find the critical numbers are where the function, where the derivative is 0, so where f prime of x equals 0, or where f prime of x does not exist. So in this case, because it's a sine and cosine, the function always exists. So all we have to do is do the first part. So we set 2 cosine of x minus 2 sine of 2x equal to 0. And then we have to use the trig identities. So I'm looking for a calculus book here that actually has a thing in the front, which I've got a newer edition that does. So we go to the trig identities and look up what are our possibilities to change the sine of 2x into something in terms of just x. So looking in there, we see that the sine of 2u is 2 sine of u cosine of u. So trig identity says the second part can be broken into, so we have the 2 here, and then we have another 2. 2 sine of x cosine of x, and that equals 0. So with that trig identity, we can factor out a common term, which turns out to be actually 2 cosine of x. So we get 2 cosine of x, that leaves 1, and that leaves 2 sine of x, and that equals 0. Okay, so it looks right. So there's 2 cases where this goes to 0, when the cosine of x equals 0, and where 1 minus 2 sine of x equals 0. Okay, so we can solve for the sine of x. We'll get the sine of x is equal to 1/2. So now what values of x between 0 and 2 pi is the cosine of 0? Okay, so that one, I'm going to draw my little unit circle. because it's going to be on one of these axes. So this is pi over 2, this is 0, this is pi. This is 3 pi over 2. Remember, the cosine is the x value. So where is x 0? X is 0 here, and x is 0 there. So for this part, we can say the cosine of x is 0. So cosine of x equals 0 when x equals pi over 2 and when x is equal to 3 pi over 2. Then we have the second part, where is the sine of x equal to 1/2? Well, we might be able to use the unit circle, but we're going to use the reference angle. I'm going to use theta, and then we'll come back and call it x after we've done everything. So remember, the reference angle is equal to the inverse sine. Again, we use inverse sine because our original expression involves the sine of the absolute value of 1/2. So make sure your calculator's in radians. And so mine is in radians, that's good. So we do the inverse sine of positive 1/2, which is 0.5235 radians. Let's convert that to some percentage of pi. So we divide by pi and multiply by pi. So 0.5235 divided by pi is 0.166 pi, which is pi over 6. So that's the reference angle, which of course is in the first quadrant, because everything's positive in the first quadrant. Now you go back to find out what the actual solutions are in the different quadrants. You look at the sine of the first thing here. All students take calculus, so the sine is positive, which is what is here, positive 1/2, in Q1 and Q2. All of them are positive in quadrant 1. The sine is positive in quadrant 2. So it's quadrants 1 and 2. So because of that, we know that the solution, I'm just going to put x. So x, our first quadrant solution is just pi over 6. It's equal to the reference angle. Our second quadrant solution is going to be equal to pi minus, we could call that for x reference if you wanted to call it. I guess I could have waited to call it x in a second. But so you get pi minus pi over 6, which is 5 pi over 6. So now we've got these two. These are critical numbers. They're critical numbers, possible minimums and maximums, and then we have these two. Okay, so I said I was going to do this short way. The short way would be to now evaluate the second derivative. So evaluate f double prime of x at these x values. So what do we have? We want, let's find what is the second derivative. Well, the second derivative is this equation. So we have to, well, we don't have to actually do anything. We can just plug it into our calculator. So we don't have to do any, because we're not looking for points of inflection, we're just evaluating the second derivative. We can just plug it into there. So let me put that in my calculator. So we have -2 times the sine, and what do we have? Pi over 6 is the smallest number, so pi divided by 6 minus 4 times the cosine of 2 times pi over 6. And I get -3. So let me put this, let me do a separate page. So what we do is f double prime of pi over 6. We're going to do f double prime 5 pi over 6, f double prime of pi over 2, and f double prime of 3 pi over 2. Those are the 4 critical numbers. So again, put them in your calculator. Make sure you're doing them correctly. So I get -3 or -3. Okay, I'm going to go insert 5 times pi over 6. And the cosine of 5 times pi over 6. And I get -3 here. If I go back and put pi over 2, which would be 3 pi over 6, that's just so I don't have to change my calculator. 3 pi over 6, I get +2. And if I go back and put in 3 pi over 2 would be the same as, well, I'll just change 2 in the denominator. So it's 3 pi over 2. Just trying to minimize changes I have to make in my calculator. And I get 6. Okay. And I didn't put these in quite in the right order. So let me move this one. Move that one down. So that in numerical order, that's the way it would be. The smallest would be pi over 6, pi over 2, 5 pi over 6. Okay, so you can see it goes minus, plus, which is what you would expect. So what does this mean? It means this is, so the conclusions we can make from these values of the second derivative are that this is concave down, which means that this one's concave up, which means like that. This is concave down, which is that, and this is concave up, which is that. So, different color here. So it means that at pi over 6 we have a maximum, because it goes like this. Then we have a minimum. At pi over 2 we have a maximum. 5 pi over 6 and we have a minimum at 3 pi over 2. So that would be the end of the problem as far as being able to get what they're asking for. I'm going to go ahead and find the points of inflection. But before we do that, let's just look at this function and confirm that that is actually the solution. So I'm going to open up the graphing program. And I'm going to share it. And I'm going to get the camera. Okay, so there we go. We're all ready now. I'll enter the function. And the function was 2 sine of x plus cosine of 2x. 2 sine of x plus cosine of 2x. Okay. And let's go from, well, I don't know exactly what it's going to come out as. Not sure. I think it goes from -2 to +2 at the most. We're going to go from y equals, oh, no, that's wrong. X goes from 0 to 2 pi. And y goes from, let's go from -2 to +2. It probably goes between 0 and 1. No, actually it didn't. It goes more than that. So let's change the y value to -4, something like that. There we go. Okay. And then we'll take a picture of it. Okay, there it is. So, and we can close the camera. Okay, so let's put this on one page. So the question was, we have minimums and maximums, and let's just identify them. So we have a maximum about there, we have a minimum there, we have a maximum there, and we have a minimum there. Okay, so now we go down and look at the y values. So, Oh, yeah. Sorry. Actually, I'm going to delete this thing. Delete the page because I forgot to put it in terms of pi, so it wasn't showing up where I want it to show up. So I need to go back and redo the graph. So I'm going to do this quickly. Change the x-axis to be in units of pi, and okay, get my camera, take a picture of the graph again. Okay, now we're back again. So let's try it again. So again, we still have the same thing. We have a maximum, a minimum, a maximum, a minimum. Okay, let's see where they are. So here we are at 1.66. So this is pi over 6. Here we are. This is 0.5 pi. So this is pi over 2. This is 5 pi over 6. And this is 3 pi over 2. So those are the three critical numbers we came up with. And you can see we have a max. It's concave down. We have a minimum, concave up. We have a max, concave down. We have a minimum. So let's make sure that's max, min, max, min. Max, min, max, min. So there you go. Concave down, concave up, concave down, concave up. Everything works out. Now, I'm going to do the points of inflection, which are probably going to be about right there, there, somewhere in the middle there, and probably somewhere. So we should have 4 points of inflection as well. So let's go ahead and do that. So I'm going to add a page. Need the second derivative. There it is. Copy that. Paste that. So to find the points of inflection, we'd set the second derivative equal to 0. So 0 is equal to negative 2x minus 4 cosine of 2x. So we can divide by 2 and divide by negative 2. So we'd end up with the sine of x plus 2 cosine of 2x equals 0, just by dividing by negative 2. I put this on the left-hand side because I'm a left-hand, I like this to be on the left-hand side. Okay, so then we look for a trig identity that involves cosine. And there's 3 different ones, but we're going to pick the one that involves the sine so that we can factor that. So the one that we would use is 1 minus 2 sine squared of u. So we get 2 times 1 minus 2 sine squared of x. And that equals 0. We multiply that out. So we'll get plus 2 minus 4 sine squared of x equals 0. And we'll put in the order of the exponent. So we have 4 sine squared of x minus the sine of x. So I'm dividing by negative 1 as well. Minus 2 equals 0. Okay. It's 4 sine squared of x minus sine of x minus 2. Okay, so that looks correct. So now we can factor it. So you'll probably get 2 times the sine of x and 2 times the sine of x. So they multiply together to give you 4 sine squared. The reason I did that is because I think you're going to need that to get that in here. So, did I do something wrong? Oh, I dropped a 2. No, I didn't. I divided by 2. Okay. The reason I'm thinking is just I'm not sure if I get. I seem to be messing something up here. Maybe it is 4. Because 2 is not going to work. So let's try 4. So we'll have 4 sine of x, sine of x, and then we'll have, so that'll give you 4 sine squared of x, and then we have, still coming out with a, maybe it isn't nice, maybe it's not nice and easy. Let's just check here. I mean, we can still factor it. It may not be a nice factorization. So, let me zoom in on this thing. So, looks like possibly could be pi over 3. This could be possibly Okay, let's go back here. Let's double check everything. I'm going to go back and check the second derivative, make sure I did that right. Negative 2 sine of x minus 4 cosine of 2x. Okay. Sine x minus 4 cosine of 2x is that equal to 0. 5 by negative 2. Use the trig identity. Sine of x plus 2 minus 4 sine squared of x equals 0. Okay, I don't see anything I've done wrong. So let's use completing the square, but what we're going to do is we're going to use x instead of sine, and then we can fix that later. So let's see what happens. So we have 4x, this is equivalent to 4x squared minus x minus 2 equals 0. Okay, so how do you do completing the square? Well, you would factor out a 4, so you get 4x squared minus 1/4 x, and I would take 2 to the other side. Okay, so you take negative 1/4 and you square that, which would be positive 1/16. So we add 1/16. So yeah, I think this just comes out to some weird stuff. So 1/16 there. So that's completing that square. We're actually adding 4/16. So we add 4/16, which is a 4th. So then you make that square a complete square, which would be x minus 1/4. Quantity squared is equal to 2 1/4. So let's convert that to a fraction. So that would be 8 9/4. Okay, divide both sides by 4. Get 9/16. Take the square root, so you get x minus 1/4. You get the square root of 9/16, which would be 3/4. And then you add plus or minus 3/4. Actually, maybe it does work out. Okay. So then you have x is equal to 1/4 plus or minus 3/4. And so that's x is equal to 1 or negative 1/2. So what that would say is you have the sine of x minus 1 and the sine of x plus 1/2. And we're going to multiply by 4 to get back to the original expression that had 4. So, we're going to multiply by 4. So let's multiply it out, make sure it works. So you get 4 times sine squared of x, and you have minus 1 plus 1/2. So you have you get minus 1/2 sine of x minus 1/2. Okay, negative 1 times 1/2 is negative 1/2. You get negative 1 plus 1/2 is negative 1/2. Okay, then you multiply it out. And actually, that's not the original equation, so what did I do wrong there? What I do is I get let me go back here again. The problem is if I multiply by 4, I get 4 sine squared x minus 2 sine x minus 2. And I don't have that. So did I? Okay, let me just check it back again. 4 sine squared x minus sine x minus 2. Okay, do that. Add to x squared minus 1/4 plus 16th. Well, take 1/4, negative 1/4, we square it, we get 1/16. So, oh, I forgot to divide that thing by 2, didn't I? That was my problem. Okay. Glad I checked it. Okay, so come back up here. I messed that up. It's just not amused. You take negative 1/4 and divide by 2, and then square it. So that's going to be negative 8. Negative 8 squared is negative 6. So you get 1/64. So we get 1/64. And so this is equivalent to adding 1/16. Okay. Now we're here. We're good. X minus so you take x minus an 8 and you square that. This is negative an 8 in there. And over here we get 2 1/16, which is 33 sixteenths. Divide by 4. You get 33 64ths. Take the square root to get x minus 1/8 is equal to plus or minus the square root of 33 over 64. So x is equal to 1/8 plus or minus the square root of 33 over 64. So x is equal to, oh, we just got that. So let's put it in decimal form because that's not going to be any kind of nice number. So 1 divided by 8 plus square root 33 divided by 64 and 1/8 plus square root of 33 divided by 64 is 0.843, and the negative solution, so we subtract that and we get negative 0.593. Okay, so what does this all mean? It means that the original equation can be factored to the sine of x minus 0.843 times the sine of x plus 0.593. And that equals 0. Okay, so the two solutions here are that the sine of x is equal to 0.843 and the sine of x is equal to negative 0.593. So we're going to use the reference angle for both of these. This is going to have answers in quadrant 1 and quadrant 2 because it's positive, and this is going to give us ones in quadrants 3 and 4 because it's negative. So we can already do that. So we calculate the reference angle, which is the inverse sine of 0.843. Okay, so we have the inverse sine of 0.843, and you get 1.0028. And if you do the same thing over here, the inverse sine of negative 0.593, you get, actually you don't do a negative, you have to take the absolute value, almost forgot that, so 0.593, so let's do that. The reference angle is the inverse sine of positive 0.953 when I take the absolute value, and I get 0.647, 0.6348, 6348. That's radians. Okay, so we divide, multiply by pi. So our reference angle for the quadrant 1, quadrant 2 solution, so let's do it here. So we divide by, take the answer, we divide by pi, we get 0.202. 0.202 pi, and the second case, we take 0.6348, divide by pi. Oh, that was the first one. Okay, so this is 0.202 pi. The other one is 1.028 divided by pi. 1.028 divided by pi is 0.319. 0.319 pi. Okay, so for quadrants 1 and quadrants 2, our answers are going to be x is equal to 0.319 pi and x pi minus 0.319 pi, which is going to give you 1 minus 0.316 is 0.684, 0.684 pi. Over here we get third and fourth quadrant solutions because this thing was negative, and so we get pi plus 0.202, so x is equal to 1.202 pi, and our fourth quadrant solution is 2 pi minus 0.202 pi, so we get 2 minus 0.202, which is 1.798 pi. Okay, so those are our values where the second derivative equals 0. Those are possible points of inflection, and we can make the table up, but since the thing's taking so long anyway, all we're going to do is we're now going to look at the curve and see if that's true, if it comes out to be right. Hopefully I didn't mess something up here. So the first one is 0.32 pi. So here is 0.4 pi, here's 2 pi, 0.3 pi would be somewhere right in the middle. So we're saying it's about right there. Okay, so that one matches up pretty closely, doesn't it? So 0.3 pi. So we're saying point of inflection right there. So it changes from concave down to concave up. Okay, the next one was 0.684. So let's go down. 0.6, 0.7, 0.68 would be about right there. There it is. Okay, that one worked out. Then we go back again. Third quadrant solution is 1.2 pi. So we go down to here. There's 1.2. There we go. And the last point of inflection is 1.8 pi. So we go over here, 1.8 pi. Ta-da! Okay, so that did work out. Thank goodness. I don't know what I don't want to re-record the whole thing again. So let me kind of summarize what I did here. We wanted to find the possible points of inflection. So we took the second derivative, set equal to 0. I divided by -2 to get that. I used a trig identity to get this. I then ended up with this quadratic type equation. So I put x in there instead of the sign of x just because it's easier to manipulate. And I decided to use completing the square. You could have used the quadratic equation if you wanted to. So I factor out a 4, so that gives me x squared minus a fourth. You can see if I multiply this out, I'll get 4x squared and negative x. I take the constant, move it to this side. It becomes positive. I take the coefficient, divide by 2, and square it. Gives me a 64th. So I add a 64th to this side to complete the square. That's the same as adding a 64th times 4 to the other side, which is a 16th. So 2 plus a 16th is 33 sixteenths, because 2 is 32 sixteenths. My term in here is negative 1/8, so that's the completing the square term. So I end up with this when I collapse this down to a complete square. Divide by 4, take the square roots, I get plus or minus the square root of that, and then I add 1/8 to solve for x, which is really the sine of x. So my two solutions are the sine of x is equal to that or equal to that. So I refactored it, put the 4 out front, and if I solve, I get these two equations which I have to solve for the values of x, where this is 0. Because if this is 0, then this whole thing is 0. If this is 0, then the whole thing is 0. So I know because this is positive, it's in the first and second quadrants. Because this is negative, it's in the third and fourth quadrants. So I use the reference angle to find the first quadrant solution. Take the inverse sine because that's sine, inverse sine because that's sine. I ended up with these answers, 0.319 pi and 0.202 pi. The first quadrant solution is just the reference angle. The second quadrant solution is pi minus the reference angle. The third quadrant solution is pi plus the reference angle. And the fourth quadrant solution is 2 pi minus the reference angle. So I get these 4 values of x, which are where the second derivative equals 0, which is where I have possible points of inflection. And I could have made up the tables. You know, I'm not going to fill in the tables. I'm just going to show you what the tables would be if you were to set them up. And you would set them up after you get to this point. So if I were to set up a table for the first derivative, I have 4 critical numbers, so I have 5 intervals, and I need a column. So I need to make a table. And let's see, it has 4 rows, and it would have 4 critical numbers plus 1 plus 1. Okay, so that would be it. And the way you would label the table would be, of course, these are intervals. You go from 0 to, in this case, pi over 6, pi over 6, to pi over 2, pi over 2 to, actually no, you go to 5 pi over 6, which is the next larger one, so you go to from pi over 6 to 5 pi over 6. No, right. It is, I'm sorry, it is pi over 2. So you get pi over 2, pi over 2 to 5 pi over 6, 5 pi over 6 to 3 pi over 2, and 3 pi over 2 to 2 pi. So those will be your intervals. And then you do the test points, and you know, test point, you'd have the sign of the first derivative, you'd have the comments. So you have to pick some test points in there, which would be kind of a pain. So that would be how you set up the first derivative table. If you did the second derivative table, then you'd use these as your breaking point. So you go, I'm not going to write it out, you go from 0 to this number to that number, that number to that number, that number to that number, that number to 2 pi, and you'd end up with 5 intervals, just the same number of intervals as you do critical numbers. So if you're still around, congratulations. That's all I have time for. Okay, we're going to number 5. So the function for problem number 5 is equal to x squared plus 1 divided by x squared minus 1. Now, probably they don't actually want us to, they probably want us just to use the curve, the picture of the curve. So let's go ahead and I'm going to plot it and bring it in so we can see what's going on. So we have x squared plus 1 divided by x squared minus 1. And let's graph it. There it is. Let's take a picture of it. Okay, so there you go. That's the function. Let's put it on one page so we can see it better. So from a concavity standpoint, just looking at it visually, we say, okay, the inside of the curve is pointing in this direction. That's up. You know, so here's the horizontal line. So if it's above the horizontal line, then it's pointing up. Here, it's pointing. This is the inside of the curve. So this is actually pointing down. Here, it's pointing down as well. Inside of the curve. Inside of the curve is that way, which is great. And so this is up. Then it's down between those two things, and then it's up there. So it goes concave up, concave down, concave up. Okay, so that's how we do it graphically. Now, as far as doing it otherwise, well, we need to take the second derivative, which is not super easy because we have to use the quotient rule. So, but sometimes you got to suck it up and do it. So I'm doing the change it to h of x because I want to use the quotient rule. Okay, so what is f of x? That's the numerator. Okay, let's check and make sure I'm recording here. It's going to take a while. Okay, so f of x is the numerator, x squared plus 1. G of x is the denominator, which is x squared minus 1. So the derivative is 2x, and the derivative is 2x. So when we plug that into the quotient rule, we take this, f prime of x times g of x, and we add or subtract g prime of x times f of x, and we divide by g of x squared. Now what's going to happen is you're going to have 2x cubed and minus 2x cubed. So those drop out. Then you're going to have minus 2x and minus 2x. So the numerator becomes negative 4x. Negative 2x minus 2x is negative 4x. And then we end up with that in the denominator. So that's the first derivative. You can see if we set the numerator equal to 0, x equals 0 is where we have a critical number right there. That's where we have a 0 slope, so that don't make sense. But you can see there are no other minimums and maximums. There are, this goes to 0, the denominator goes to 0 when x equals 1. That's why we have these vertical asymptotes. And in terms of the derivative does not exist at x equals negative 1 or 1. So that's the first derivative stuff. Now the second derivative, we have to do it again. So we'll just, let's call f of x the numerator, and g of x the denominator. And I think just to make it easier, I'm going to multiply out g of x instead of using the chain rule. So you'll get x to the 4th minus 2x squared plus 1. So it's just using FOIL. Using FOIL on that second thing. Okay. So we just say derivative of negative 4x is negative 4. And the derivative of this is 4x cubed minus 4x plus 0. So if we take the second derivative, we still use the quotient, same kind of arrangement, so we take this times that minus that times that. So we get x to the fourth minus 2x squared plus 1 times negative 4 minus negative 4x times 4x cubed minus 4x. All divided by g of x squared, which is, well, I'm going to put it back in its original form. So you get x squared minus 1 squared. Squared is for the fourth power. Okay, let's see if we can figure out what's going on here. So we're going to have negative 4 times that, and negative, okay, that works out right. So really we're looking for where the denominator is undefined. So where the second derivative is not defined, which is at negative 1 and positive 1. Because if we factor this, if you factor the denominator, you'll get x plus 1, x minus 1. So you can see the denominator goes to 0 at those two values of x, and that's why we have the vertical asymptotes. But that's also why the first derivative does not exist there and why the second derivative does not exist there. So those are possible points of inflection as well. And so let's multiply this, just the numerator out. So we get negative 4 times x to the fourth plus 8x squared minus 4. And then the second part you'll get negative times negative is positive, so we get plus 16x to the fourth minus, because we have negative times negative is positive, negative. So 4 times 4 is 16, x squared all over the denominator. Okay, so what else can we do here? So you get 12 x to the fourth minus 8x squared minus 4. So we divide by 4, because we're going to set this equal to 0. So we divide by 4 and we get 3x to the fourth minus 2x squared minus 1. 0. 3x squared x squared. So this is going to be plus 1 minus, is that right? Minus 1. 3x squared times x squared is 3x to the fourth. 3x minus 3x squared plus 1 is negative 2x squared, and negative 1 times positive 1, okay, so that's 0. Now this has no roots, so we don't get anything out of there. And secondly, we can factor this, and we get x minus 1 and x plus 1 is equal to 0. So this is telling us we have a change in second derivative. We have a, so not only is that a point of interest because of the fact that there are vertical asymptotes there, but also because the numerator goes to 0 at those points as well. So, and you can see that's what happens. Here's the vertical asymptote, and we're concave up here, we're concave down between negative 1 and positive 1, and then we change to concave up. And you can tell that by, if you took a value like negative 2 and 0 and positive 2 that are in these intervals, then you could see whether the second derivative is positive. If the second derivative is positive, then it's concave up. So let's just do that. Let's go back to, the denominator is always going to be positive because it's raised to an even power. So all I have to do is look at this, or this, and it's find out is that positive or negative for various values of x. So the easiest one is x equals 0. Then we don't want to set it equal to 0. We're saying, you know, the second derivative is equal to, or proportional, I guess, because I divided by 4, so it's proportional. And so if this is positive, then the second derivative is positive. So you plug 0 in there, and you get fw prime of x is negative. And if you put x equals negative 2 in, you'll get 3 times negative 2 to the 4th minus 2 times negative 2 squared minus 1. Okay, negative 2 to the 4th is 16. 16 times 3 is 48. 2 squared is 4. 4 times negative 2 is negative 8 minus 1. See, that's going to be positive. So in the interval less than negative 1, the second derivative is positive, which means it's concave up. Here it's down, concave down. And then if you did x equals 2, you'll get the same kind of deal. You get the same exact number because this will be positive. These are even powers, so this 2 to the 4th is the same as negative 2 to the 4th. So you'll also get, whatever you get, 39. You'll get 39 here, and it'll be, that's positive, and therefore it's concave up. So we go back to our diagram. You can see it's concave up until negative 1, then it's concave down between negative 1 and positive 1, and then it's concave up after that point. Okay, this is problem 6. This is a function, and here's the curve. You can see the curve in the book. It's just slightly different scale. So visually, what we would see is it's concave up until we get to about right here. And then it curves the other direction, so it's concave down. And then at 0, it switches, and it's concave up until about this point, and then it's concave down again. So we have concave up, concave down, concave up, concave down. Okay, let's prove that's correct. So we're going to take the derivative of this, and so we'll get y prime is 1 over 270 times negative 3. Okay, I'm going to take the derivative here. So the derivative is going to be negative 15x to the 4th plus 120x squared plus 135. So that's the first derivative. And then we're going to take the second derivative, which is, we still can leave this fraction out front. So now we take the second derivative, so you'll get negative 60x cubed plus 240x, and that's it, because that goes to 0. So there's the second derivative. And we set that equal to 0 to find where the concavity might change. So this part we don't have to worry about. I'm just going to solve the top one. So if we divide by negative 60, we'll get x cubed minus 4x is equal to 0. So 240 divided by 60 is 4, and a negative sign gets there. Okay, we can factor out an x. So we don't want to cancel out the x, we want to factor it out. And so we get 3 values of x, where the second derivative equals 0. We get 1 at x equals 0. So let's just try them here. X equals 0, x equals negative 2, and x equals positive 2. So there's x equals 0. There's x equals 2, negative 2. Here's x equals positive 2. So we see we're concave up because that's the inside of the curve. Here you can see the inside of the curve spinning the other direction now, so it's going in that direction, so that's down. Here we're going up, concave up, and then we have concave down. And it says that they change at x equals -2, 0, and +2, which is the case. So to answer the question, we can say that the open interval from -infinity to -2 is concave up. And we can say also that from -2 to 0, it's concave down. And from 0 to +2, it's concave up. And from 2 to +infinity, it's concave down.